Hello and welcome to session 3 of the TAC Webinar 2023 series. I'm Divya Wagner. I lead the technical services team in the Americas. And on behalf of Arista TAC, we want to say thank you to all of you for taking the time to be with us this morning. Our goal at the end of this session is that you learn something new and you find some value from the data and the material that we're going to present today. If you're new to Arista and have never worked with Arista TAC before, or you're considering Arista as a potential vendor in your network and support is a part of that decision, then here's a great chance for you to interact directly with the Arista TAC engineers. All the presenters, the panelists, and everybody that's behind this entire program is part of the Arista TAC team. So you get an opportunity to discuss, to ask some questions and interact with customers, to interact with our TAC engineers, and these could very easily be the same engineers that you're working with at the end of a phone call if you do contact us. All right, we're also going to present two parts to this session, right? On debugging layer 3, we're going to have the CLI portion, and then we're going to also share some tips and tricks on the Cloud Vision section. So please join me in welcoming our presenters, Upasana Dangi and Tomas Glogor. Upasana is going to walk us through the CLI portion of the session, and then Tomas is going to share all of the cool tips and tricks on Cloud Vision. And today's session is actually a follow-up to last month's session where we did the first half of debugging layer 3. Today, we're going to continue on and talk about the second half of debugging layer 3. Just a quick summary to catch you all up if you are joining us for the first time. We kicked off the entire series last year in September. We covered a couple of topics, including EOS health checks, upgrades, with some flavor of MLAG involved and so on. Okay, and then this year in 2023, we have already covered debugging layer 2, the first half of layer 3, and then today we're going to wrap it up with the second half of layer 3. We get this question often, so I just want to make sure everyone's aware these sessions are recorded. They're all available. So even if you didn't have a chance to join us for the previous sessions, or if you want to share this information with others in your team, or if you just want to review it for yourself, all of the sessions are recorded. Our recording will be made available shortly after the webinar itself wraps up today. Not only that, we also have all of the collateral that is involved with the webinar, including all of the slide decks, the topology diagrams, some sample configs, and we're also going to capture all the important Q&A questions that come up today, right? And all of that will be made available to you. All of this is available on the Arista Community Central webinar page. Again, you can check the chat, and that's where you'll find that link. It's also on this slide here. During the course of this presentation, there will be commands that are being shown, right? There's going to be the topology and all of that information. Since we're going to give all of that to you, so I'm just letting you know so you don't have to, write it quickly as we go through. All of this is going to be made available to you, so just follow along. The main request that I also put forth right before we started was to make sure that you have a copy of the topology diagram ready to go. If you registered before March 20th, you would have received an email from us with the topology attached. If you have not already downloaded, you can look at the chat. There is a link there. Do take a minute to go ahead and download the topology for debugging layer 3, session 3, because that's going to make your life a whole lot easier. The format for that we've adopted for the 23 series is to actually bring up a network topology that mirrors a lot of what you may have in your networks, and we want to be able to exhibit how to go through the whole troubleshooting process in as practical a manner as possible. So there's going to be actual switches. We're going to take you through some live troubleshooting sessions, and so having the topology to follow along is going to be essential. Our presenters will be bringing up the topology and also flashing it on screen at regular intervals. If you want to take a screen capture, that's also an option that's available to you. Now, once we finish today's session, we will be moving on to a new topic, which is going to be VXLAN. So our sessions in April, May, and June are going to focus on that topic. Now, if you have any questions, feel free to post them in Q&A. We do have a number of our engineers who are panelists and will be playing a role in responding to all of those questions. We're going to do our best to be able to wrap up all of the questions. And if we run short on time, then we'll make sure that we note it down and get back to you individually. Okay. And with that, without further ado, I want to hand it off to our presenters today, Upasana and Tamas, to take you over. Okay. Thank you and enjoy.
Thanks, Divya. Hello, everyone. Good morning, good afternoon, and good evening. Thank you for joining us today. My name is Upasana Dangi, and I'm from the Arista TAC team. I'm based out of California. For today's session, we are going to go through some common issues that are seen in Layer 3 networks. And what we're going to use is the scenario basically to explore some helpful commands that can be used to verify routing states and also learn how to trace the path of the packet in the data plane. Essentially, what we want to do is go hop by hop till we can narrow down the point of failure. So here is our sample topology. It's a leaf spine topology. We have 2 sites, and on each site, we have some host machines that are connected to their respective leaf devices. The leaf devices are then connected to the local spine switches, and the spine switches are the ones that are handling the routing information between the 2 sites. To connect to these sites, we are going through an L2 transit, but keep in mind, the transit here is just an example. In your network, the transit could be a service provider, it could be a firewall, it could be any other network component, right? We are using BGP as a routing protocol between all of the switches. For routing between the sites, each spine has a 1:1 BGP neighborship with the remote spine, which is going through the transit. So for example, spine 1 is going to go and form an eBGP neighborship with spine 3, and spine 2 has an eBGP neighborship with spine 4. At present, local spines don't pair with each other. The AS numbers that we are using are all present on the devices themselves, just for your reference. And to make it intuitive, I'm keeping all of the host subnets in the 192.168 aggregate, and all of the network interfaces are going to be part of the 10.x subnet range. All of our devices are running 428.3m, and there's a quick snapshot of the platforms that we use today, just in case you want to come back and take a look at it. Once again, just want to remind you that we have posted a link to this topology in the webinar chat. So please download it so you can follow along with us during this session. All right, so let's get into today's problem statement. We have received some reports of host connectivity issues, but at this point, we don't really have any additional details. So to begin our troubleshooting process, the first thing we need to understand is our scope. This actually helps us narrow down which network component could be causing the issue. So I've done some surveying for this network, and I found that the connectivity issues that we are seeing is mostly between the 2 sites, but local host traffic is fine. So just based on this information for now, I'm just going to assume that the hosts are not the problem here, and we are going to continue to troubleshoot the network. Also, the connectivity issues that we are seeing, it's random, where sometimes the applications are able to connect successfully, and sometimes they are not. To have something tangible to track, I'm going to be using 2 sample hosts where we have confirmed the problem. So we're going to use host 1, which is 192.168.100.2, and we're going to use host 2, which is 192.168.200.2. And also to save us some more time, I've already validated that there are no adverse drops in my network in the layer 1 path between the 2 hosts, such as layer 1 errors, congestion, or CPU drops. We did actually cover all of the necessary commands for this in our 2022 webinar, which I have also linked here. And I would definitely recommend looking those up after today's session, because it's just going to help you spot any immediate red flags in your network. So coming back to our topology for today, since nothing immediately is standing out, we still have to narrow down which network component is contributing to our problem. And so to do this, we are actually going to have to follow the path of the packet and also perform some additional layer 3 checks to figure out where the problem is. Just for the sake of this demo, I have pre-recorded the CLI steps that we will be going through, and I'll just walk you through them as we go along, right? So to start our investigation, we are going to first begin at the source. I'm going to first check the connectivity between host 1 and host 2 with a simple ICMP test to see if there are any losses. So with that, let's try to ping the destination host 2, which is 192.168.200.2. I'm just going to give an arbitrary interval and send about 10 packets. So here I can see that my ping test is working, and I'm not really seeing any packet loss. But this does not mean that the network is fine. It just means that whichever path in the network the ICMP packet hashed to is okay. I just want to point out that Arista does use flow-based ECMP hashing by default, which includes source and destination IP, source and destination port numbers, along with protocol to generate that entropy. Since ICMP traffic does not have port numbers, it's always going to use one link in that ECMP path. So if I want to make my flows take multiple paths, I'm going to need some application traffic. Since at present, my applications are not running any active traffic on them, I'm just going to use telnet. Let's say we're going to use port 50,001 to emulate the TCP traffic needed. Even though each telnet session is using the same destination port, the source port is going to be chosen at random. So that still sort of gives me that entropy I need to test various ECMP paths in my topology. So with that, let's try to test the connection again to host 2, this time using telnet. So I'm going to try that to 192.168.200.2. Let's try it on port 50,001. All right, so this one seems to be hanging. I'm not getting any feedback from host 2. It could be because what host 1 sending out is not being received or processed, or the same thing is happening to the reverse flow. All right, so let's try a few more tests to see what we find. This one worked. I mean, I'm getting a connection refuse. That's just because the application's not listening on this port at the moment. But the fact that I'm seeing something here means that the bidirectional TCP handshake is able to form between the two hosts. Let's try one more. This one seems to have hung again. All right, this one worked. So based on this test, what we've confirmed is that some TCP flows are making it through and some are not. Now, in last month's webinar, we already covered the use of UDP traceroute, which is a pretty useful command to have when you want to narrow down points of failure, especially in these kinds of scenarios. But since we've already covered this method, today I thought we'll take a look at an alternative approach by tracing the physical path of the packet to narrow down the device. All right, so given that our ping works, we know that our gateway connectivity is fine. So let's move up a layer to leaf 1. Just from our diagram, just for reference, this is the device that we are going to focus on. Now, on leaf 1, if you wanted to find out how a particular packet is being routed and what are the next hops, you can use the show IP route command to be able to see this information. And from here, what we can see is that we have a two-way ECMP coming in from the spine. It's coming in through EVGP. And if you look at the prefix, we are getting an aggregate /16 from the spines. That should be okay. To confirm we're actually getting it from the spines, you can always use LLDP neighbor. So here we can confirm we have spine 1 and spine 2 connected to our next hops 5 and EV2. For any BGP route, if you wanted to see more information about that prefix, you can always use the show IP BGP command. So in this case, I'm going to do this for 192.168.0.0/16. And I'm just going to add that detail there. I'm using the /16 because that's what I'm getting from the spine. You can get more specific if you want to. When you look at this command, you see a whole bunch of information show up. A lot of the information is about the prefix attributes like the AS path, origin, metric, local pref, and a lot of other information. You can also use this output to see the routes advertisement information as well. So let's take one as an example from Spine 1 and just walk through what this means, right? The first part in this output, that is the next hop that's advertised in the BGP update to us. In our case, it's 10.1.1.1. The second output, that is the actual IP of the BGP neighbor with which we have established a session, which for us is Spine 1. And that value in the brackets, that's just the router ID of my neighbor. For me, I have Spine 1 configured as 10.0.0.1. Since this is an eBGP neighborship, you might see that the next hop and the neighbor IP is going to be the same. That is fine. Some more details that we can see in this output is it's telling us that we are receiving an aggregate. This is the aggregate for the /16 that the spines are advertising to us. We can also see that this is part of an ECMP set, which is what we also saw in show IP route. Another thing that's useful over here is the received age on the prefix. This is pretty important because it tells us if the route has been or not. In this case, the route has been pretty stable. It's been stable for about 11 days now. So let's take a look at that. And if it hadn't been that stable, basically I would have used show event monitor route in order to understand, if there are any routing loops in my network, or if this route is constantly being added or withdrawn. As we have covered in our previous webinars, the event monitor feature can be extremely helpful in debugging. So I would definitely encourage you to refer to those sessions for how you can actually use it to troubleshoot your network. Now, since we're talking about the route age, if you want to see the route age of all the routes in your routing table, and not just the routes that you have received through BGP, as we saw in this output right now, you can also make use of the show rib route IP command. So you can just use show rib route, and I'm going to get a little more specific for my subnet, but you could just leave it as is. And if you look at this output, it's going to show me all the available routes in my routing table that could apply to this prefix, not just the most specific route. And in addition to that, it's also going to show me the route age for every route that I have in my routing table. This is useful because when you're running other routing protocols like OSPF, ISIS, or even just static routes, you might want to see how long they have been stable or present. All right, so we validated that our route is present, we validated it's stable. The next few commands we are going to go through are going to help us ensure that they're programmed in hardware. Now, there are two commands I find pretty useful. One is to check the overall hardware capacity. This can be done through the show hardware capacity command. So let's actually run that on our box. This command will basically show us a raw dump of all the tables and their total resource utilization. It covers a whole bunch of features. Could be unicast routes, multicast routes, access lists, service policies, and direct flow, and just a whole bunch more, right? It's a good way to get a snapshot of how much legroom you actually have on your switch for features that are going to need hardware resources. And if any of these resources are overrun, EOS will syslog an error for that. That syslog can be trapped by your network monitoring device, just so that you can take some corrective actions on it. If you are using CloudVision, you really don't have to do anything. This information is streamed by default, and CloudVision will generate an alert for you. Additionally, we also have this ability to set the high watermark. With this, you're going to be able to generate a warning when the watermark value is hit. This can be a good way for you to get notified more proactively instead of when you've already maxed out your resources. Arista does have some default watermarks inbuilt for these tables. So for example, unicast routes, we proactively generate a warning syslog if your routes reach around 90% of capacity. I have linked the TOI for this feature in the slides, so you can go back and grab it later on in case you do want to tweak these values for something better that might work for your network. Since mine is a lab setup, I'm not actually using these resources. It's pretty underutilized. So I think we should be good and we can move on to some other checks. The second output that I find useful gives us an idea of the actual route details programmed on the ASIC itself. If you remember, we ran show IP route for the destination IP. This command just basically provides us with a software state for our destination IP. In order to see the actual hardware state, each Arista platform has a specific command to see what we will program on the ASIC. This command is tied to the chip family, so there is going to be a platform level dependency. At the end of the slides, I have linked all the corresponding commands for Arista platforms. But for today, we're just going to use what applies to our leaf 1 switch, since that's what we're using. The leaf switch that I have is a 7280 R2 device, and you can see that on your switches just through show version. So if you see it's a 7280, just for reference, all of the 7280, they come in R, R2, R3 series. They all are different generations of the Jericho chipset, but they do all have the same command that you can use to see this hardware route information. The command that we are looking for is show platform FAP IP route. Now, you might be wondering what the word FAP means here. This is a keyword that's a generic term that we use instead of having to specify the actual generation of the chip. So you don't have to keep using different statements for different models. We're just going to do that work for you. So let's run our more generic show platform FAP command for our destination prefix and see what we get, right? So I'm going to do this for 192.168.0.0/16. Okay, so when I run this command, I can see that the prefix is programmed with some valid forwarding next hops. I can see these are part of an ECMP, and they have been assigned the same ECMP index, which is good because they are forwarding to the same next hop. And we also have MAC addresses assigned as well. These are the MAC addresses that the hardware will use to rewrite the destination MAC when we route into the spine layer. If you want to validate if this is correct, you can always cross-reference this with the ARP table, because that's going to hold the actual value of the next hop based on the IP. So in my case, this does seem to be correct. So I think we should be good here as well. So now we have validated both the control plane and hardware states, and everything does seem to be looking good. So let's just follow the packet in the data plane. Now, to follow the path of the packet, Arista has multiple ways you can do this. In previous webinars, we used advanced mirroring to CPU that allowed you to mirror a copy of the data plane flow to see what the switch had received, what the switch forwarded. We also use counters bins in webinar 1 this year to track packets of specific sizes. So for our session today, we are going to use another common tool, which is access list counters, to check for traffic forwarding. Access lists are underrated but very useful, especially when you're looking at intermittent loss in the same flow, because you can use the counters from an ingress access list and an egress access list and apply it to a flow to see if those statistics add up, to see if there is any loss incurring from the switch. For today, we are going to use access lists to determine if leaf 1 is actually forwarding traffic to the spines. So I have already pre-configured 2 access lists on my leaf 1 switch. So let's take a look at it. We have TAC test spine 1 and then TAC test spine 2. They're the same access lists. They're permit only. That's because I'm just using them to count traffic, just to see if it's been forwarded. So let's take a look at the configuration of the access list itself. Right? I have counters per entry. This is needed to enable that counting on all of the rules that we're going to use. My rule number 10 is a more specific rule that I want to count for the flow that I'm testing, which is why it always is good to have a flow. You also see that I have a permit IP-NE explicitly configured to allow everything else. This is a super important step because access lists do have an implicit deny at the end, right? So just make sure you have that in there. Now, I have applied both of these access lists in the outbound direction because I'm trying to see what leaf 1 has sent out to the spine. So as you can see here on Ethernet 2 and on Ethernet 5, I have both my access lists in the outbound direction. To actually see the counters on this access list, you can run show IP access list and then just give the access list name. So for spine 1, and then we can do this for spine 2. Now, if you're like me and you don't want to run these outputs one after the other, you can also make use of the run feature that allows us to add multiple CLI commands in a single CLI command. The syntax for that would be just use the keyword run. And then you can add the first command, which is show IP access list for spine 1, delimit it to the second command, which is the same thing for spine 2. And voila, now I don't have to run these commands one after the other. If I look more closely at this output, I can also see that my access lists already have some existing statistics on them. If this is a large number and you want to clear your baseline, you can clear the access list counters by using clear IP access list counters. And you can be more specific. You can just give your very specific access list. So I'm going to do this for the spine 1. And I'm also going to do this for the spine 2 access list. In case you wanted to clear counters just for the session you're on, you can do the same command and add the keyword session. So this basically is going to keep your overall stats the same and just clear it for that CLI. All right. So now that my access lists are cleared, let's confirm our baseline is reset. That's good. And now, so that I can do my testing in peace, I'm just going to do a watch diff here so I don't have to keep running this output. So with all this set, we can go to the host and redo our telnet sessions. So let's restart these sessions again, shall we? Okay, so the first telnet didn't work. From the access list, we can see it hit spine 2. Let's try another one. This one worked. This one seems to be going to spine 1. The next test, let's see. It didn't work based on the timestamp. It is going to spine 2. Let's do one more. This one worked. Again, based on the timestamp, I see this is going to spine 1. All right. So we've learned 2 things here. 1, that the leaf is able to send packets to the spine layer. And 2, the working sessions over here, they seem to be hashing to spine 1 in that ECMP. And all of the non-working sessions that we've tried are hashing to spine 2. So with this, I think I have isolated a potential point of failure, which looks to be spine 2 at the moment. So I can move my troubleshooting directly to spine 2 and check its routing state. For reference, spine 2 is the switch over here in our topology, and that's where we are going to focus. So going to the spine 2, I'm going to quickly run show IP route on it just to see what spine 2 sees as the next hop for my destination IP. Now over here, what I'm seeing is an auto-generated aggregate route and nothing specific. This aggregate is generated because my spine 2 is configured to aggregate the leaf subnets, the whole 192.168 network. And we can confirm this by checking the running config for router BGP. I have that aggregate statement in there that's creating that aggregate route. But what I had really expected to see was a more specific route coming in through spine 4. So my spine 2 can route my traffic to site 2. I'll try to see the same output on spine 1 just to see what spine 1 is seeing. And so let's run the same IP route to host 2, which is 192.168.200.2. Here I can see what, this looks a little better. I can see the /26 coming in from spine 3, which is 10.13.13.2, coming on ET1. And we can always look at the LLDP neighbor information. It confirms that this is the interface going to the transit. So this probably is why stuff going to spine 1 has been fine so far. So with this, it looks like our problem is probably localized to spine 2 and 4. So I'm just going to move our focus there. And since I wasn't actually seeing any routes, step one is to see if my neighborship is up. In order to see the neighborship states, you can do show IP BGP summary. And here I can see that my neighborship is established, but there are a few red flags here. For starters, if you look at the timestamp of the uptime, it seems extremely recent, just like 16 seconds ago. Compare that to the 11 days of stability on the leaf neighborships, that does seem to stand out. Another thing that we can see here is that the prefix received is 0, and that definitely is a red flag. I do not expect that to happen, right? So what I'm going to do is also run the same output on spine 4, just to see what it's seeing. And it looks like it's the same behavior on spine 4 as well. Now, to save us some time, I've already done the job of validating if all my routes are correctly configured in BGP, no route map issues. And so ideally, they should be advertised correctly and received correctly by the spines. So which means that we do need to dig a little bit deeper here. Since this timestamp is recent, let's actually take a look at the syslogs to see if this BGP neighborship has been flapping or has it just been recently brought up. So let's do show logging. I'm going to trim it to the last hour, and I'm going to hunt for this particular neighborship. Okay, so scrolling to this output, it does look like my spine has been flapping for a bit now. And as I look at it, we can see that there is a certain pattern that emerges because this flap is pretty deterministic. If you see the timestamp, it's flapped at 6:07, but then it flapped again at 6:10, and then again 3 minutes later at 6:13, and then at 6:16, and it's just been doing that all along. The error that we are reporting is that the hold timer seems to have expired. Now, hold timer expiry basically just means that the BGP instance did not receive any periodic keep alives for the duration of the BGP hold timer. By default on EOS, the default hold timer is about 3 minutes, which does match the timestamps that we are seeing in syslogs. So moving our troubleshooting to the neighborship, we can get more information about the neighbor through the show IP BGP neighbor command. And you can get more specific. So I'm just going to put my current spine 4 here. So for this particular IP, we can see a whole bunch of states and info over here. A few highlights. It shows us the keep alive that's being used. So that's 60 seconds. Hold time is 3 times that. So that's 180 seconds. We can see that this neighborship is still pretty current. And as from the syslogs, it's because of hold timer. That was the last cause. Since we didn't get any prefix, I'll also want to check if there were any prefixes dropped due to BGP policy violations. Everything seems to be 0, but a few policy violations are AS path detection, first enforced AS, malformed packets, and so on, right? So let's keep digging. All right, so we see something important here. We see that the total number of TCP retransmits are present, and this is non-zero. It usually indicates that there is some missing packet in the TCP stream. In order to understand what's actually missing, we are going to have to physically see the packets that are being sent and received by spine 2 and spine 4. Since these are control packets, we can easily capture them by running a TCP dump on the interface where the BGP session is established. So on spine 2, that is Ethernet 1/1. Let's just go back to the diagram just to see where that is. That's the one connecting to transit. Since my BGP is flapping every 3 minutes, I am going to actually favor using something called as a background TCP dump session instead of running a live one. This is extremely useful if the problem that you're debugging is infrequent or it's unpredictable. This way you can just run a rolling TCP dump session in the background and save the captures to a file and terminate it even after the event is seen, right? We can also set a maximum file size for the captures so the older files can get log rotated so we can protect our file system space, even if you have to run this capture for hours or days. So it sort of helps us make this safe to run in production. To actually configure the session, we are going to have to go into the configure mode. So let's just jump into config. If I can type it, so config, and the syntax for that is TCP dump session. And then you can give some arbitrary name to the session. So I'm going to give BGP spine. The next thing is to actually select the interface you want to run the TCP dump on. For us, it's Ethernet 1/1. Then you can specify the file count, which I like to use. What this basically does is it creates mini PCAP files based on the number you have set. And the oldest PCAP file is going to start getting log rotated when you hit the max file size. So for me, I'm using 10. So I'm going to create PCAP 0 through to PCAP 9. And I'm going to set the max file size on it, which basically says, if you hit this limit, start log rotating. For us, I'm going to set it to about 50 million bytes. That comes up to 50 MB. And I'm going to specify a location for this to actually get stored in. So just going to save it in Flash, name it something like spine2.pcap. And because I know I'm troubleshooting BGP, I'm just going to filter out all the noise and just capture packets that are destined to BGP. So it's going to be port 179 on this box. All right. So when we hit enter, we can see that the BGP session already exists. That's because I have already gone ahead and configured this for us. You can see that through show TCP dump. In this, you can actually see the session name, you can see the target interface, the space you're saving it into, and any filters if you've applied on it, right? I've also done this on Spine 4, so we can actually compare one specific stream between the two of these boxes. So same thing over here. And to save us some time, I have already pulled the PCAP from both of these switches so that we can all compare the data together on this session. So with that, let's just go to the PCAP itself. And I've just taken a snapshot here. Let's focus on one TCP stream. Let's take a look at it on Spine 2's PCAP. If you look at this, we can see that the TCP handshake for this BGP session seems to be fine because we can see the SYN and the SYNAC and the ACK sort of go through. And so this makes me think that maybe the layer 1 path is okay. And if you go further down, we can see the BGP open message is also being exchanged from both the neighbors. BGP open is the message that we use to negotiate and validate the BGP neighborship. This is what will get us into the established state, which we are in our switches. But if you look at the little blob on the red on both the PCAPs, right? Somewhere our BGP updates seem to be hitting a snag. We are seeing a lot of retransmits for the BGP updates. Updates are the ones that carry the actual prefix information. We can see that all of the updates that Spine 2 generated that were destined to Spine 4, if you see in the bottom PCAP, they're not actually seen here. And conversely, whatever Spine 4 has been generating that's destined to Spine 2, if you go back up, it's not seen here. So this makes me suspect that perhaps the transit is dropping the packets. And this might be forcing us to withhold the keep alives, which is ultimately taking down the BGP session. Also, if you look at a common motif over here, the packets that seem to be getting dropped are larger on the MTU size. So there is a possibility there is an MTU component to this, because all of the smaller packets in our BGP session, they seem to have made it through. So before we actually take a look at that whole transit network, first, let's actually take a look at what is the MTU that we have configured on Spine 2 and on Spine 4. So let's see, we can use show IP interface brief. And I can see that my transit facing interfaces are MTU 9000 and my host subnets are basically on 1500 MTU, which is expected and fine. Let's see and compare this with Spine 4. So if you do show IP interface brief, we can see again the Spine transit is 9000 but the host facing MTU is 1500. That's also okay. But so it looks like both my spine facing MTUs are matching. But we should always remember that even though we match our local interfaces to the correct MTU, if there's any other component in between, we need to ensure that the end-to-end MTU also allows this configured size. Now, based on the PCAPs, I do suspect MTU is the cause here, but I don't actually have proof yet. So I'm going to try to prove this without actually having access to the transit. The easiest way to do this is through a quick ping test. So I'm just going to run ping with the default MTU size initially, which is just the default ping size between spine 2 and spine 4 on the IPs that they're appearing on. So I'm just going to add ping for 1024.24.2. Mine is a layer 2 transit, so it doesn't matter. But if you had an L3 provider or an L3 next hop, it's also a good idea to set the don't fragment bit to test the path MTU, just because in this case, BGP actually goes out with the don't fragment bit set. So just for this session today, I'm also going to set it, but for L2 transit, it wouldn't have mattered. So let me ping this particular IP. It all seems to be working. So far, so good. Now let's try with the BGP packet size that was failing. So we look to our PCAP for an example. We saw 1562 was failing. So let's try something closer to that. So let's see, we tried 1560. This one is failing. Let's go a little lower. Let's go to 1500 because this does make me think that my transit is actually dropping packets with MTU. Let's go to 1500. All right, so this does seem to work. Let's go a little above. This failed again. All right, so it does look like my transit might be configured for an MTU of 1500, and that's causing it to drop my BGP updates that have exceeded this limit. Now, to solve this problem, I can either configure my spine MTUs to match that of the transit, which is 1500, or if I cannot change that value, I need to check with my transit vendor and fix the MTU on their side. So for this lab, I'm actually going to fix it on the transit so we can check if the larger packets can actually make it through. So let me go and work that transit magic. I'm going to just fix it on the transit side. And let's see if this made any difference at all to our BGP neighborship, right? So once the transit side is done, on our switch side, we can run the same show IP BGP summary command to see the neighborship statistics. The quick stats. All right, nothing has changed yet, but let's give it some time. Okay, so now everything else is the same, but I am seeing the number of prefixes received has come to a value that I expect in my network. I'll do the same thing on spine 4. Okay, so they both seem to be seeing routes. Let's see what the route to the destination IP looks like now. So let's do to 200.2. And okay, so now I see the actual route that I expected from spine 4. That's 1024.24.2. And with this, I think, even on the host side, we have confirmed that, the telnet sessions are working, irrespective of where they're being hashed to, as I'm testing. So let's just do a quick test as well. So you see all of these, the handshake has completed. It's not really caring about which link it has hashed to. So in this case, that was our problem. So let's just, quickly recap what we did here. So on the host side, we saw some telnet sessions that were forming and some that were failing. On the leaf side, we use access list counters to determine that the telnet worked when we were hashing to spine 1, but all of the non-working sessions were basically hashing to spine 2. When we went on to spine 2, we confirmed that while the BGP session with spine 4 was up, it was flapping every 3 minutes and no prefixes were being learned. So we used TCP dump captures to actually look at the BGP packets. And we confirmed that BGP packets were being retransmitted, and the ones that were being retransmitted were greater than an MTU size of 1500. This was causing our spines to withhold sending the keep alives and that was ultimately tearing down the BGP session due to hold timer expiry. When we fixed the MTU on the transit, the BGP neighbors were able to come up. Well, they were already up, but they were able to stay stable. They were able to learn all the prefixes, and that's what fixed our connectivity issue. I've also put a list of the commands that we ran today just for a quick snapshot reference, so you can use that later. Now, one thing to note here is that if my number of network prefixes were low, I might have actually not even hit this issue if I was initially bringing up this network. This could be something that could slowly creep in to my production network if my learn prefixes suddenly increased, right? Like EVPN neighborships, where you can suddenly have a whole bunch of routes that you will learn. Now, additionally, today we discussed this from a BGP perspective, but this is actually very common also from the data plane perspective, because if my host side MTU was also greater than 1500, then at the application flow level, I would see degradation, which would sort of look intermittent to the user. This is because the smaller packets in my flow probably would get routed successfully. But then when I had larger packets, they would start to get dropped. And so it might just look like, like the host applications were just hanging midway, right? From the TAC side, this is a very common scenario that we see in VXLAN environments because, with VXLAN, we have to account for the additional VXLAN header, just because the VXLAN headers are marked by default with do not fragment. So typically it is recommended to increase the VTEP uplinks to a higher MTU to sort of accommodate this extra header size. But here, even if we put the correct MTU on the VTEP, if we do not confirm the end-to-end path between the two VTEPs is allowing that MTU, you might start to see intermittent issues, same ones that I mentioned for the host networks, right? So that is why, from our side, we always recommend that if you are changing your MTU size, just run an end-to-end ping test with a don't fragment bit set for the highest MTU that you have configured on that particular path, just to make sure it makes it through. So that way, after your initial setup is online, you don't see any random unexplained issues later on in production, right? So this sort of ends our CLI portion of the debugging. I hope that was helpful. I have linked some of the helpful articles and commands for various platforms over here for your reference. But with that, I'm going to hand it over to Tomas, who's going to walk through this scenario just, from the Cloud Vision point of view. So over to you, Tomas.
Thanks, Upasana. That was a great demo. So hey everyone, my name is Tomas. I'm from the EMEA TAC team, and today I'm going to show how useful Cloud Vision can be to troubleshoot such scenarios. In case you have missed our previous webinars and you're new to Arista, Cloud Vision is our multifunctional NetOps platform that you can use for real-time telemetry, automated network deployments, including zero-touch provisioning, network-wide upgrade orchestration, compliance and risk assessment, and many more, both on-premise and in the cloud as our SaaS offering. So let's get started. I'm using the same topology as Upasana and would like to state the problem description again. So we got a ticket from our apps team saying that one of their applications is having trouble communicating with a client, but another app is working just fine. And they have identified the two flows. The working flow is sourced from 192.168.100.2, which is host 1, and destined to 192.168.200.2, which is host 2, and using TCP 60001. The broken flow is between the same two hosts, but it's using TCP 50,001. They also said that ICMP works fine, but SSH and other UDP TCP-based apps don't, and they've noticed that this was a while ago at around 2:05 p.m. And as we've shown in previous webinars, flow tracking can be really useful for initial troubleshooting. So I've also made this video to not rely on the demo god. So let's go to Cloud Vision and see how that can be helpful. So if we access the topology page, we can see our network here. We can see our two leaves. We can see our 4 spines. we can see the two hosts, and we can also see the transit. And we would be also able to access the list of flows at the time our colleagues were trying to access the application. And since we store historical data in NetDB, we can go back in time to that specific time range and see how the flows look like, which is super, super cool, as you won't need to ask your app team to run further tests at this stage. Otherwise, you'd have to ask them again and look at how things are happening in real time. And of course, you can do that as well, but it's really nice that you can go back in time and check the network state and flows at that time. So let's just go back to 2:05 p.m. And to do that, you can either use the slider in the timeline at the bottom of the page and drag it to 2:05, or we can also use the time picker, which might be easier, and then select 2:05 from there. And then after we've done that, we can select a time range. So for instance, we could select 30 minutes in this case, let's say, and hit apply. And so now if we click on the flows on the top right, we can see here all the flows that the switches are streaming to CloudVision, and we could check those two flows that our colleagues were talking about. So first, I'm going to check the one that is working, which is when host 1 talks to host 2, and the source and destination port is TCP 60001. So if we click on that flow, as we can see, host 1 is able to talk to leaf 1, and then leaf 1 is able to send the traffic to spine 1. And then in this case, the traffic is getting hashed to spine 1, which then goes to the transit, lands on the other side of spine 3, goes down to leaf 2, and finally ends at host 2. So now let's take a look at the other flow. If we click on back to flows list on the top left, and then select the second flow that uses TCP port 50001, we can see from here that host 1 is able to talk to its gateway, which is leaf 1. And then we can see that leaf 1 hashes that traffic to the other spine 2. However, after this, we can see that everything stops. And on the CLI, Upasana showed us how access lists can be super useful to understand which spines is the app traffic getting hashed to. Now we saw how streaming flow tracking to CloudVision and using topology flows can help us achieve the same. And you just need to click on the flow and then see at which hop the traffic stops. Note that this is a very small topology just for the demonstration purposes, but at scale, this can save you tremendous amounts of time to find the flow of the path, as opposed to having to go hop by hop. And now that we saw where the flow stopped, let's take a brief look at the routing tables. So we can either go to the device page, which you can select from the top, or you can also click here on the device and then click on the device overview hyperlink on the left pane. And then you can go to the IPv4 routing table. As in this scenario, we're using IPv4, but you would do the same for IPv6 if you'd use IPv6. So going back to the IPv4 table, here we'd want to check the destination subnet, which in our case is 192.168.200. And we can see that it's actually missing. So we are not learning it from the remote end. And if we check the other spine 1, which you can select from the top, we can see that this has the prefix installed, which is why we don't have issues when the traffic gets hashed to this link. You might have noticed that if you switch between different devices, let me switch back to spine 2 here, and then to spine 3, then you can see that the filter actually persists across these devices, which can be helpful when you want to check the same filter across multiple devices. Otherwise, you can remove it and look at the other routes or filter on some other prefixes. And now before we move on, as a side note, I just wanted to show here that when you look at the next hop, so for instance, if we click on this next hop IP, you can actually see to which device that IP belongs to. So if I click on 10.13.13.2, it goes to the endpoint search page, and then you can see from here that this one is actually belonging to spine 3. So now that we have that, let's go back to spine 2. Why are we not learning that prefix of the destination host subnet? So let's try to do some more detective work here. So the next thing I do is to check my BGP states that we can do in a few ways. We can, for instance, look at the BGP tab under the device page. So if we click there, then that has some good information. However, today that might not have all the necessary information for every scenario. So in that case, thankfully, we have dashboards where we can build custom views with arbitrary states, either using natively available metrics, or we can also use advanced query language or custom query language that can read data from NetDB. And in this case, I've used a combination of both. So if we go to the dashboards page, and actually before checking any of the dashboards, I wanted to give a shout out to our Help Center feature. So here you might have noticed that we have this Help Center button on the top right, which has been around since 2022.1.0. If you haven't upgraded yet, you're definitely missing out. And through this feature, we are aiming to promote self-help and aid users in learning and getting started with Cloud Vision features faster via detailed steps, images, and sometimes even animations. And for instance, in here, you can learn how to view dashboards. If you click on the view dashboard hyperlink, it will go to another article, and you can see how to view the dashboards. You can see how to configure dashboards, how to import them, export them, and much more. And it's pretty useful. You have also AQL in here. And we are working on adding a Help Center on each and every page, and your feedback is very welcome, which is why we have this feedback button on the top right that you can click on and leave your feedback with us. All right, so let's take a look at these dashboards, shall we? So I've made a few dashboards. I've labeled them with Palantiri, so some Lord of the Rings Easter eggs for you there. And if we click on the BGP states, I've built these dashboards that contain a few information. For instance, it has the BGP session status, and this one shows you the session status for all the spines and leaves. In this case, we have 12 sessions, and I also built something similar to show IP BGP summary, which is this other table, BGP session details in the default VR for all devices. And so you can see that this is not just for one device. You can see that this is for spine 1, leaf 1, and spine 2. So it's for all devices that actually match this pod name tag. And in dashboard, we also have tags and can be useful to filter specific devices. So in our case, I have two pods, pod WB, which contains leaf 1, spine 1, and spine 2, and then pod WB2, which contains leaf 2, spine 3, and spine 4. So let's take a look at the BGP session details here. If we go back to pod WB, we can see that all our sessions are established, which is cool. That's what we want. That's what you want. But then if we start looking into the last three, especially at the last three columns, which are very useful because we can, for instance, see the uptime, and we can see how many prefixes we have received and accepted. Here we can see that on spine 2, we have received 0 prefixes and accepted 0 prefixes as highlighted in red, which is another cool thing in custom dashboards, is you can set up color mappings based on single values or integer ranges or strings. And we can also see the uptime, which is very small, which is just a few seconds compared to the other sessions, which have been up for a few hundred hours. Yeah, so it's 11.9 seconds. So here we could also use the timeline and actually see how long the sessions last. So if we bring up the timeline on the bottom, which can be hidden sometimes, but you have that arrow on the bottom, and if we try and go, for instance, a bit more to 1408, we can see that the uptime is now 2 minutes 53 seconds. So maybe move it just a bit more, and we can now see that it's 55 seconds. So we are sure that it has reset again. And we know that the issue is still present, so we're going to check the other dashboards to get some more information. So let me scroll down a bit here. I've created this other dashboard, which is called BGP flaps, where I've written a small note that ideally you should have none, but if you do, you should light the warning beacons of Gondor because something is on fire. And then you can check here this table that shows you the flaps for the last 4 hours, but this is customizable. You can actually choose how many hours you want in your query. There we can see the spine 2 that has this amount of flaps, which is in this case 80 in that time period. So now to get a bit more details, we can check the next the table next to this, as the note says above, check for more details in the BGP session historical state tracker and arrows pointing to the right as well, where we can select each device separately and see how many times the state has changed on each session. So as we can see, spine 2 and spine 4 as well has had a lot of state changes. So if we go check spine 2 and make sure to select the time column in sorting in a descending order, if we scroll down, we can see that the states have been changing what it seems to be every 3 minutes or so. So between spine 2 and spine 4, which could give you an idea that the whole timer is expiring. And then if we go further down, I've added here a dashboard for BGP syslogs that is using regex to match on BGP, so BGP only syslogs. And we can actually see here that the whole timer is expiring. And if we look at the timestamps again, so we have the whole timer expired event there, that's at 10:25. Then if we scroll down a bit, we have the same at 10:28. And then if we scroll more, we have at 10:31. So yes, the whole timer is expiring indeed. And the whole timer is by default 180 seconds or 3 minutes. And obviously we can also check the events. So if we go to the events page, or there can be also added to dashboards, but you can also go to events and filter on the device. So in this case, we are filtering on spine 2. And then from this, we can see all the events that happened for spine 2. So we can also see here that the BGP states have been changing every 3 minutes or so. And there here on this page, we also have a help center, and it shows you how you can configure event generation, event notifications, custom syslog events. And these are very, very useful, especially the event notifications, as you can set up alerting to your favorite third-party platforms such as Microsoft Teams, Google Chat, Slack, email, Opsgenie, PagerDuty, and even syslog and SNMP lately. So you can get alerted if something happens, so you don't need to stare at your screen all day long. And another cool thing I wanted to mention is we could have taken a look at some other metrics as well. So if we go to the dashboards page and search on that tag again, we could have taken a look at the interface metrics, for instance, because in most cases, BGP would flap due to a layer 1 issue. So you'd also want to check your interface statistics. So if I click on this other dashboard called interface monitoring, we'll see here that we have some stats for discards in and out, FCS error rates, operational status, TX faults, RX loss events, and so on. This is a non-exhaustive list. You can add much more here. And we can see that everything looks okay, basically. And there's another very cool feature that's worth mentioning. So if we go back to dashboards, then you can, if you select multiple dashboards, there's this action button that appears on the top right, and we can actually create a timed loop, which is called the rolling dashboard as well. And once you do that, it asks you for the dashboard display duration. So let's set this now to 15 seconds just for the demonstration purposes. Then we can put this on a huge screen, especially if you are in the NOC center. This can be very, very useful, as you might be able to spot things that are changing and turning red. So in this case, it would go through the BGP states. It then would go to the next dashboard, which is the interface monitoring. And then it would go to the third useful dashboard, which I've built for TCAM capacity, which is what Upasana was showing on the CLI as well. And then on this one, you can see if something is red or not. So now that we've gathered all this information, we should have a good idea of what's going on. And as the next step, we would now go and take a packet capture as Upasana did, or run some ping tests to check the MTU on the CLI. We could also actually do some more cool things here with change control actions, and you could initiate some some ping tests from change control actions. That can be very useful in many situations, as we've seen in previous webinars. And with that, our demo ends. Hope it was very useful and informative. And before handing it over to Nile, just wanted to mention that we've also added some helpful articles and some more screenshots of the slides as well, but we'll have the recording ready for you to watch it again at your own convenience. But if you have any questions, then please do reach out to us. Back to you, Nile.
Thank you, Tomas. Hello, everyone. This is Nile Parekh. I am one of the managers in the technical services team based out of California. First of all, thank you very much, Upasna and Tomas, for the deep dive and covering this topic in such good detail. There were some really great technical pointers that we touched on, and I hope this session was useful to everyone who did attend. As a reminder, the recording of this webinar will be uploaded at the same spot on the Arista Community Central, along with the configs, topology, and all the good discussions that we are currently having on the Q&A chat. Now, moving on to the announcement for the next Arista TAC webinar, the fourth session of the 2023 series is scheduled for April 26th, same time, 11 a.m. Eastern. After doing a deep dive on layer 2 and layer 3 debugging topics in Q1, we are now shifting gears. We are prioritizing the feedback that we received from all of you, and we will be focusing on some more concrete technical topics. We will now get into the exciting world of VXLAN debugging, focusing on the traffic flow through a VXN fabric and all the intricacies in troubleshooting that. I would say please do share the registration link with your colleagues and others within your network who might benefit from these sessions. It will be the same link and it will be the same webinar login. Also, I would, of course, highly recommend people to join in live, as we have another set of great speakers eager to walk you through this very popular topic of interest around VXLAN. I did want to do one quick plug. There is a short feedback form which is linked in the chat here. Please take a few minutes to share your thoughts. We are always keen to hear feedback. We would want to know if this was useful, what we could do more, what we could do differently, and your feedback plays a huge role as we plan the future sessions. And for people who have been providing feedback, thank you. We very much appreciate that. This encourages us to keep putting together more troubleshooting scenarios that is going to be beneficial to all of you. And I see some open questions, so I'm going to keep the webinar open for a couple of more minutes as the Q&A is still ongoing in the background. We do have an excellent panel here, so continue to post your questions, and we will keep this on for a couple of minutes for things that have not been answered yet.